Thank you, Dennis. So something that really is sort of related to that previous section in terms of insulation R values is the issue of situations where one wants to put more blown-in insulation in an attic to the degree that there would be a tapering of the insulation depth at the perimeter. This depends on a number of factors. Of course, it depends on the steepness of the roof, but it also depends on the specifics of the roof structure. So, for example, rafters typically set directly on the top of the wall, and therefore there's limited space near the perimeter. And this is also true for some types of trusses, sometimes referred to as conventional or an overhang truss, where even though there's a truss, the top cord is perhaps directly at the top of the wall. Other types of trusses, cantilever trusses, the top cord comes down and connects with the bottom cord out at the position of the eaves, if there are eaves, and that actually causes the roof structure in the top cord to be at a higher position above the wall and better accommodate insulation thickness at the perimeter. So, and that's a function, of course, of how large the eaves, how deep the eaves are in terms of the further out you go as a starting point, then you get a higher position for the roof. Also, so let me come back to this in a moment. So if we have a situation where there is no taper, then the R value would be constant across the attic surface, including at the perimeter, and the R value converted to a U value to calculate the heat flux would then be constant. So, for example, an R50 would result in a U value of 0.02 as indicated here, and on the x-axis I'm showing the distance from the edge of the building, from the exterior wall inward into the attic. And so in this case, with no perimeter effect, then we have U of 0.02 and uniform heat flux. However, if we have taper at the perimeter, then we can see additional heat flux, and even though the R value is being reduced in a linear fashion in the tapering region, the U value, which controls the heat flux, 1 over the R value, is increasing at a greater rate than linear, and so that can contribute to the significance of this effect. Finally, so we've implemented this in BEopt, and what you'll see on the input screen is a D-rate factor that applies to the R value for the entire attic area. So that's also influenced by the type of roof. If there's a hip roof, then there's perimeter on all sides of the attic, whereas a gable roof essentially has the tapering effect at the front edge of the roof and the back edge of the roof, but not on the gable ends. The magnitude of this effect in terms of the effective R value or the D-rated R value for the attic area is also a function of how much insulation we are talking about, the depth of the insulation. Obviously, a modest insulation depth may not have taper, but if we want to really put a lot of insulation into the attic, then the tapering effect and the perimeter area that's impacted becomes larger as the nominal insulation depth is increased. So I'm going to try going out to BEopt and show you what this looks like. provided I can find the right version of BEopt here. Well, that didn't really work. Okay, so here we have an example. All of those parameters that I showed on the left side of the screen are really available in BEopt. So, for example, on the geometry screen, if you go to the level where we have an unfinished attic here, we see inputs for roof type, either gable or hip roof, the roof pitch. So we might say that this was say a ranch house with a shallow slope to the roof, and if we said that it had rafters or the rafter style truss, then we get a situation like this. So that's a lot of the geometry, and then of course we've drawn the dimensions of the building that influence how much impact there is on the overall attic effective R value. So if we go to the option screen and look at unfinished attic, the unfinished attic category, what we will see is for various ceiling insulation options here, there's a new display variable in BEopt that is the roof taper factor as a function of the eave depth. So 0 eaves or 1 foot deep eaves or 2 foot deep eaves are here. So if we came down to, for example, this option, or let me go to this option, R60 blown in fiberglass. So that is that's a lot of depth of that insulation, and in this particular case, and I made this a little bit extreme by making a shallow tilt to the roof, etc. But this is saying that there would be a 0.71 factor or a 0.29, 29% D rate. Now, if we come up to, in some instances, we will see that the D rates are more when the, let's see, I think what I should actually do here is go back and let's say that I had cantilever trusses. Then what I'm going to see is in the case where the eave depth is larger, there will be less D rate than when there's not so much. So in this case, we see instances where if I have a 2 foot eave, then even with my shallow roof, I have an 8% D rate, whereas if the eave depth is 1 foot, it's 16% D rate or 29% D rate for 0 eaves or for the rafter style that sets directly down on the roof. So, so this is, all of this happens pretty much automatically in BEopt based on the geometry screen inputs.